Hi everyone, welcome to Professor Long's Lectures in Anatomy and Physiology. I'm Professor Bob Long. These videos are intended for use by students who are enrolled in my Human Anatomy and Physiology course. We're in the coronavirus shutdown. I'm sure you've heard my disclaimer before. So we're doing some face-to-face teaching, but I have to present it online since we can't all be in the same room. All that social distancing stuff. I'm so sick of coronavirus, I'm sure that you are too, but we still have to mention it. So, these videos are done rather crudely. I'm shooting on a board that's in my dining room. If you hear noise in the background or a dog barking, I apologize. I'm not going to edit it out. I'm just going to keep going. These are all one-take videos. Anyway, this particular video is going to be a continuation of our visual physiology series. This video is not entirely testable material. The beginning of it, I have to teach you about the nature of light, at least from a non-physics standpoint, so to speak, so that we can understand how light functions, what pigments are, so that we can understand visual physiology and how we see. This is a very basic explanation with some real fundamentals and some simplified concepts. So all you physics whiz out there, don't send me ugly emails or messages. I understand I'm kind of simplifying it. Anyway, let's get started. So we need to understand what is called the nature of light. How does light behave so that we can understand how vision works? So think about this. If I have a light bulb, a source of light, when light is shot out of a little light bulb, it is shot out in bundles of energy that are sometimes referred to as particles of energy that we refer to as photons. Photons are a type of what is called electromagnetic radiation. They're a type of radiation. Now, when photons are shot out of a light source, they appear to travel in a straight line. There's actually what we call the dual nature of light. Light is both a particle and it's a wave. And what happens is, as a photon of light is shot out into space, it's going to travel in a wave-like pattern. If I average these waves, then this photon of light is going to travel in a particular direction. The direction that the light is traveling in, we refer to as a ray of light. But it's a photon traveling in that direction. So sometimes I use the terms ray and photon interchangeably. Now it turns out that because they don't travel in a straight line but in a wave form, it turns out that a particular photon of light, when I study its wave pattern, turns out that if I measure the distance between the crest of one wave and the crest of the other, or the peak of the waves, which is very often abbreviated with this symbol, which we refer to as the wavelength. I'm going to use that symbol a lot. Okay. But that distance, or the length of that wave for this two waves, should be equal for every other wave for this particular photon of light. All of these wavelengths, or if I just use a little d for distance, that distance between the crest of two waves, or that wavelength, is the same for all waves for one photon of light. Now, a second photon might travel at a longer wavelength. So if I measure this distance, it is a different distance than the wavelengths of a different photon. Now the reason this becomes important is because the length of the wave is inversely proportional to the amount of energy that the photon is traveling with. Okay? We can talk about the speed of light, but all light particles in a vacuum travel at 186,000 miles per second. That doesn't mean anything to us, but each particle or photon of light is traveling with a different wavelength or a different amount of energy. So one of the things we know about light is the higher the wavelength, the lower the energy. Okay, they're inversely proportional. If one goes up, the other goes down. Now, what we call white light, I'm going to draw a different light bulb here. If I have a whole bunch of white light spreading out, turns out that in that white light, I have all of these different wavelengths. Some of them are visible to our eye that will trigger visual physiology. We call that the visible spectrum. And some of them are of wavelengths or velocities that don't trigger vision in our eye, so they lie outside what we call the visible spectrum. What does that mean when we use that term? Well, it turns out that when we study the wavelengths of light, or the energy with which they're traveling, we kind of assign colors to some of them. For example, In white light, what we would call white light, which is coming out of a light bulb or basic sunlight, when we look at white light, it actually has a combination of all the wavelengths. So there's going to be some red light in here. There's going to be some orange light in here. I don't really have a yellow marker that shows up very well, so I'll use this funky looking green, but there'll be yellow, green light, blue light, indigo, and violet light, all mixed in to what we call white light. All the photons of all these different wavelengths are all traveling together. Now, if I take a specialized piece of glass that we call a prism, if you're a big Pink Floyd fan, you know this is the cover of a Pink Floyd album. Anyway, when I shine white light through a prism, it turns out if the glass is designed properly, then it can separate out the different bands of light based on their wavelength. It's almost like if I had a filter that had big holes and smaller holes and even smaller holes all next to each other, and I had rocks falling into it and I'm shaking it. All the big rocks will end up in one pile as they fall through a big opening, and then smaller rocks and smaller rocks. So we can separate out the wavelengths of light by shining it through a prism. And they'll look like this. In one area, I'll get all the photons in the red part of the spectrum traveling next to each other. And then I'll get all the orange ones, which are smaller wavelength, next to each other. Then I'll get all the yellow photons next to that, traveling in a band. Then I get the green photons traveling next to that. And then I'm going to get blue and indigo and violet. And these are the colors of a rainbow in order. Red, orange, yellow, green, blue, indigo, which would be kind of like a turquoise color, and violet. Okay? And it turns out that we can measure the distance of the waves of these different colors of light. And it turns out that red light has the longest wavelength in what we call the visible spectrum. So if I were to measure these wavelengths, all of the red photons are traveling at a particular wavelength or with a particular amount of energy. And it turns out that those are somewhere around 760 nanometers. A nanometer is a billionth of a meter. So imagine if you took a meter, you cut it in 1,000,000 smaller pieces, that would be called, or 1,000 smaller sections we call a millimeter. Each one of those, if you divide it into 1,000 smaller sections, would be a micrometer or micrometer. If you took a micrometer and you divided that into 1,000 smaller subunits, you would get a nanometer or a billionth of a meter. While it's tiny, it can be measured. Turns out that red light is traveling somewhere around 760 nanometers, and that blue light is somewhere around 420 nanometers. Okay, these numbers might be a little bit off, but not much. Okay, now there are types of electromagnetic radiation that are traveling at a higher wavelength than 716 nanometers. For example, up here we would have infrared, and we would have radio waves, and they have even longer wavelengths. And anything smaller than purple light or violet light, we would call ultraviolet radiation. We have X-rays, which are very high powered, and we even have what's called gamma radiation, which can be used for other types of visualizing internal parts of the body, MRI, CT scans, and other things. Okay, so now, since these wavelengths are not going to trigger vision, and these wavelengths are not going to trigger vision, only these are, this is referred to as the visible spectrum. Okay. Everything outside the visible spectrum is not part of the visible spectrum. We call this the visible spectrum because spectrum means a broad range and visible means it's going to trigger visual transduction. We can see this light. We cannot see this type of radiation. I hope that makes sense. Now, next concept. I'm going to leave this here. I'm going to erase some of this information up here, okay? Imagine if I shoot BBs out of a shotgun. we fire a shotgun, the BBs don't all travel next to each other in a tight bundle like they were packed into the shotgun shell. Over time, they start to spread out. And the further out we go, the larger the cone becomes. And now I have BBs traveling like this. Okay? And if I fired them at a wall some distance away, maybe at a paper, like a paper target, I would actually see the spray of shotgun holes in the paper. Now, if I measured the velocity, the speed or the intensity, the energy with which these BBs are traveling, the ones traveling in a straight line would be traveling at a higher energy or have a greater impact than the ones traveling at angles. And so imagine this. Imagine if I set up a cardboard wall, a thick wall of cardboard, some distance away. And imagine that some of these are traveling at such a high velocity, they blow right through the wall. Some of them are traveling at a velocity that they get embedded deep in the wall, others less deeply. Some might make a dimple and bounce off, and some may not even impact the wall at all. Okay. So each one of these BBs is traveling with a different velocity, just like these photons are traveling with a different velocity or impact, energy. So they're going to all have different impacts on whatever they hit. Okay. So now, that's kind of what this is doing. Now let me give you one more concept, okay, and then we'll move on. So now, imagine I have some kind of tennis ball machine or a baseball machine that's going to shoot baseballs or a tennis ball out of one end, like a little tennis ball cannon. And let's say that I have a big cardboard wall back here, and I have people standing in front of it, and these people can catch. Let's say I have a 5-year-old, and then I have a 10-year-old, and then I have a 15-year-old baseball player or softball player, someone who's 20, and so on. So I have all these people trying to catch. If I fire this ball at a certain speed, I might shoot it soft enough that the 5-year-old can catch it. This is going to represent a photon. If the energy of the photon can be absorbed or kind of caught by another object, we call that a pigment. Now, if I fire a tennis ball a little bit faster, maybe the 5-year-old can't catch it. It might be too fast for him, but the 10-year-old can. So this would be pigment 1. This would be pigment 2. If I fire it even faster, it might get past both of them, but this one's going to catch it. So now I have a third pigment. If I fire it too slow, nobody could catch it. If I fire it too fast, maybe none of them catch it, and it gets absorbed here and embedded in this wall. Okay? And maybe I fire something so hard it blows right through. These cannot be absorbed. These cannot be absorbed. This is outside of our visible spectrum. Not enough energy, too much energy. This would be our visible spectrum, and we have different pigments that can absorb photons of different energies or wavelengths. Okay? Anything that can absorb the energy of a photon of light and trap it, kind of catch a photon, so to speak, is considered to be a pigment. I hope that makes sense to you. So if you're trying to follow along in my notes, then if you switch to page 15, we can define what a pigment is. I hope you have this concept in your head. Not all photons of light can be absorbed by substances, but if a substance can absorb a photon of light in the visible spectrum, we call that substance a pigment. Some pigments can absorb the photons of low energy, some pigments can absorb the photons of medium energy, and some can absorb photons of high energy. Okay? I hope that makes sense. So we're going to have different visual pigments. So now, in your notes set on page 15 near the bottom, it says define a pigment. This is where your notes for lecture tests begin. Everything else here just helps us understand this. A pigment is any substance that absorbs the energy of a photon of light, or of a photon. Okay? And usually we're talking about within the visible spectrum because we're talking about visible light. Okay? Now, there are different types of pigments in the eye. One of the things that's listed next in the note set is what we call the pigmented epithelium. And I'm going to get into this, what the pigmented epithelium is in the eyeball, but essentially it is a layer of cells that can absorb those photons of light that are outside the visible spectrum. So if you remember all the people I had drawn here and I had the cardboard wall would represent our pigmented epithelium. If the photons catch it, it's going to get absorbed by that wall, so to speak. I'm going to talk more about the pigmented epithelium, and we'll define it a little bit later. On page 16, it asks you to draw the visible light spectrum. We've done that. And that's just for us to kind of understand different wavelengths and energies. But it asks you to list the 4 different pigments of the eye. So now that I know this is my visible light spectrum, I'm going to erase part of this, and I'm going to list the 4 pigments that are found in our eyeball or in our retina. Those that are going to absorb in the red part of the spectrum, all the way up into the yellow and the green a little bit, this pigment is called iodopsin 1. Iodopsin 1 is in the red part of the spectrum, or it absorbs photons that lie with wavelengths in the red part of our spectrum. There's another visual pigment in the eye that will overlap this, and it absorbs almost 100% of these, and some of these it can't catch. That's why we draw it as a bell curve. But this pigment is called iodopsin 2, and it absorbs photons in the green part of the spectrum. The third visual pigment that we're going to see, and it overlaps with the other 2, but it catches optimally or absorbs optimally those in the blue part of the spectrum, those photons in the blue spectrum, so we call that iodopsin 3. They absorb the blue photons, or the photons in the blue part of the spectrum. There is a 4th visual pigment that can absorb any photon, almost all of these, okay? But it's optimized somewhere in the middle here, but this pigment is called rhodopsin. So there are 4 visual pigments. Iodopsin 1 absorbs maximally those photons in the red part of the spectrum, or in the of red wavelengths. Iodopsin 2 catches photons or absorbs photons that are in the green part of the spectrum, and iodopsin 3. Rhodopsin can catch any of the visual pigments, but rhodopsin is far more sensitive. It only takes 1 or 2 photons to trip rhodopsin, where iodopsin 1, 2, and 3 require more photons to hit them in order for them to trigger a visual transduction cascade. You'll see what I mean in the next video when we talk about this. I'm going to refer back to this. But imagine this. If you've ever been to a carnival and they hand you a softball to throw, and you're trying to knock the little milk bottles or the bowling pins, those aren't very good bowling pins, but you know how they stack bowling pins on a table, and you toss them. Let's say there's only 1 bowling pin here. Okay? If you hit it with a softball, the bowling pin might wobble. If you could throw a second softball while it's wobbling, then you might knock it over. This represents the photon. The bowling pin represents one of these visual pigments. Rhodopsin is so light sensitive that 1 or 2 photons can change its shape and trigger visual transduction. Now let's say those 1 or 2 photons are in this part of the spectrum. If this were iodopsin 1, it's going to take more photons to make it trigger. If 1 hits it, it'll wobble a little bit. A second one hits it, it'll wobble more. Another photon and another photon, and then eventually it gets knocked over. While it's already wobbling, we have to keep hitting it and hitting it and hitting it. What that means is we need a lot of photons to trigger the iodopsins. We need bright light here. Here, I only need 1 or 2 photons. So I can trigger rhodopsin in dim light or in a darker room. If it gets too bright, all the rhodopsins get knocked over or triggered, and they get bleached out. They won't function any longer. That's why when you're in a bright room, we don't see a lot of the rhodopsin pigments aren't functioning. They're bleached out. If I start to make it darker and darker and darker, the fewer photons that are bouncing around in a room, the darker I make it, the less these are going to be triggered, and I'm not going to see color. I will then start to reactivate my rhodopsins and trip them, and reset them and knock them over, reset them. So we see, in a dark room, we don't see color or great detail. We can see shades. So we know that rhodopsin does a lot of black and white vision, or what we call night vision. We know that cones do our color vision. There are two different types of cells that we're going to be looking at that are found in the retina. Two major classifications. Cones can contain iodopsin 1, 2, or 3, and rods, which contain rhodopsin. So I'm going to describe the difference between a rod and a cone, and then I'm going to stop there, and we're going to go on in another video and do retinal organization. So now, we've done most of page 16. You can read about rods and cones on page 16. We did a little bit of the bottom of page 15. Now I'm going to draw a rod and a cone, and there's a part on page 15 where it asks you, draw and describe the difference between a rod and a cone. So, you know what pigments are, you know about iodopsin 1, 2, and 3, and rhodopsin, and the visible light spectrum. So let me erase all of this. And in order to keep these videos shorter, I'm gonna cut this video here, and I'm gonna start a new video where we start to just draw and describe rods and cones. They load much faster into YouTube, and I think it's better for y'all to watch shorter videos and keep your attention span. So, I hope this was helpful. I hope you learned something. I hope you had as much fun as I did doing this stuff. And I'll see you on the flip side in the next video. Thanks for watching.